Hi, how's it going? So this is more on sentential derivations. We're now on slideshow 16, and this is section we're going to talk about 6, which is the official rules of sentential. So a couple things you might want to have with you. There's something posted on Moodle called the derivation rule sheet. You're going to want to look at that. What we're going to do in this video is go through rules 1 through 8. So this is on the first page of the derivation rule sheet on the left-hand column. That's what we're going to talk about right now, although I'm going to introduce them in a slightly different order than they're in on that sheet. Okay, so let's talk about the rules here, and I'm going to have a little drink here. Okay, get some sponsorship revenue here maybe if we do this right. Okay, so here's the basic idea. Our system is broken into what we call in rules and out rules. So why are they called that? Well, an in rule, the idea is that it tells you how to introduce into your derivation a line that has that connective. So for instance, our or in rule will tell us what ingredients you need to sort of derive an or statement. That is a statement that has an or as its main connective. It tells you how to introduce that into your proof, so it's called an in rule. An out rule, on the other hand, tells us how to break down a formula or get out something out of a formula that's got a certain connective. So for instance, our or out rule, which we've already seen in the last video, tells us how to take a formula that's got an or as its main connective and get something out of that. It's an out rule. So ideally, we'd like to have an in and an out rule for each of our connectives, each of our 5 connectives. That is and, or, if then, if and only if, the biconditional, and not. Turns out, though, you don't actually need all 5 such rules. So what I want to do here is walk through the 8 rules that you do need, again on that left-hand side of that handout, and just try to explain how each of those works here. So let's talk about the out rules first. So the first one we've already seen is arrow out, and there's 2 forms. There's the modus ponens and the modus tollens version of that. Let me just write them down here and just make sure we understand again how those work. So arrow out has 2 forms. This is the modus ponens form of arrow out. It says, if you know that A arrow B, if you have an arrow, and you also have the antecedent, you can derive the consequent B. But it's got a second form. It says, if you have an arrow, A arrow B, and you have the negation of B, the negation of the consequent, you can get the negation of A. So that's our arrow out rule, and it's got 2 forms here. And again, I hope we can see why it's called an out rule. It tells you how to get something out of an arrow. In this case, it says you've got an arrow and you have one other ingredient, you can get something out of that. So that's our arrow out rule. Let's also look at our or out rule, which again we've seen before. It says if you've got something in the form A or B, and you happen to have the negation of A, the first one, you can derive B from that. And there's a second form also. It says if you know A or B, and you know that not the second one, you can get the first one A. So again, I hope it's clear why that's an out rule. It says if you've got an or statement, and you have got this extra ingredient, you can get something out of it. So those 2 rules we've seen before. To those out rules, I want to add 2 more. The first is called and out, and the second is going to be called biconditional out. So let's look at and out. And out says if you know that an and, oops, that's not an and, that's an or. It says if you know that a formula of the form A and B is true, from that alone, you know that A is true. And that should sound plausible to you. If I know that it's both Monday and it's raining, then I know that it's Monday, without any extra ingredients. So it's sort of an out rule in the sense that it tells you how to get something out of a statement, in this case an and statement. But it's slightly different than these out rules, which require 2 ingredients. This one only requires 1. And we have a second form of this rule also. which just tells us also if you happen to know that A and B is true, you can also conclude that B is true. So basically it says you can take either the first part or the second part and break it down, take it out of that and statement. That's and out. Finally, we've got our biconditional out rule, which we don't use as much, but we do have it. And it says if you know that A biconditional B is true, then you know that just A arrow B is true. Why is that? Well, if you remember, the biconditional really says if A then B and if B then A. It says both of them. That's what the biconditional says. And this basically says, so if you know that you get an arrow going both directions, you can get it going one direction. And the second form of the rule just makes explicit that we can get either direction of the arrow from a biconditional. And again, this is an out rule. It tells us how to break down or get something out of a biconditional. And it is like and out in that it doesn't require an extra ingredient. Okay, so those are our out rules. They tell us how to break formulas down and get something out of them. And their names are based on the things that they break down. So arrow out breaks down an arrow, and out breaks down an and, biconditional out breaks down a biconditional, and or out breaks down an or. Let's now talk about our in rules. Okay, so I'm going to erase these and write down our in rules, of which there are 3, and then one special rule we'll call double negation. Okay, the first in rule I want to talk about, we haven't seen any in rules yet, is and in. So how does and in work? Here's how we write it down. And in says, look, if you have on one line A, and you have on some other line B, then you can put those together with an and between them. That is, if you know that A and you know that B, then you know that A and B. And that should seem really intuitive. That should seem exactly how and works. The only thing to note here is that we also add a second version of the rule, which tells us that we can put A and B together in any order we want. So that is, if you know A and you know B, you can conclude either A and B, or you can conclude B and A. The order doesn't matter, essentially. And again, notice this is an in rule in the following sense. It tells us how we take some formulas that don't have and put them together in a way that now we do have a formula that has and. It tells us how to introduce an and formula into our proof or our derivation. We also have a rule we'll call biconditional in. And what this one says is the following. If you know that A arrow B, and you know that B arrow A, then you know that A, if and only if B, that is A double arrow B. And hopefully that's very intuitive given what we know the biconditional is. The biconditional just is both arrows. And again, we have a second version of the rule that tells us we can write it down in the opposite order. So it looks like this. So we write down the rule 2 ways just to say, look, from A arrow B and B arrow A, you can also conclude B if and only if A. And again, we have to write them down both ways, because remember, these are syntactic rules about the form of the rules, not about what the formulas themselves mean. And so that's why we have to write them down both ways, just to say that we've got both instances of those rules. We've got one more in rule and then double negation. So the last in rule is called or in, and it tells us how to introduce an or an OR claim into our derivation, and it looks like this. So it says, if you know that A is true, you know that A or B is true for any B whatsoever, even if it hasn't appeared in your proof before. And that always strikes people as a little bit odd, but if you think about it, I hope it makes sense. So if you know that A is true, then no matter what B is, you know that either A or B is true because you already know that A is true. And that's what this rule says. It says no matter what B is, once you know A is true, you know that A or B is true. And we also write down two versions of this rule to indicate again that order doesn't matter. So we say if you know that A is true, you could also write down B or A. So order doesn't matter for this rule. So here's our three in rules. Again, they tell us how to introduce into our formula, into our proof or our derivation, either an AND formula, a biconditional formula, or an OR formula. The last rule we need is one that I gestured at in previous videos, and that's called double negation, or DN. And this works exactly how you'd think it would. It says if you know that A is true, you can get not A. That is, for any formula, you can put two negations in front of that formula. And it says you can also remove two negations. So if you happen to have a formula with two negations in front of it, you can take those negations off, and the rule you cite is DN. All right. Those are all our rules. And it turns out those are the only rules you need to derive every single valid argument in sentential. We're going to introduce some other rules as we go on. If you look at your handout called derivation rules, you'll see there's some additional rules on that right-hand column. Those are rules that make things easier. They make our lives, they make our proofs go a little bit quicker, but they're not strictly speaking needed. All we need are the 8 rules I just introduced. So before we stop this video, let me just say a few things that are important to keep in mind about these rules. First, the thing to notice is that some of the rules have 2 inputs, so like this. AND in has 2 inputs. It says you need to know that A and you need to know that B to conclude that A and B. Some rules, like OR in here, only have 1 input. It says once you know A, you can derive A or B. And here's the important thing to remember. If a rule has 2 inputs, if it requires 2 inputs, or 2 ingredients if you like, then whenever you use that rule, your citation needs to cite 2 lines. So if I'm ever going to use AND in, there always has to be 2 lines cited. For instance, 1, 2 AND in, because there's 2 inputs. If a rule only has 1 input, like OR in, then the justification, that is the citation on the side there, only should cite 1 line, because it only has 1 input. That's the first thing to keep in mind. The second thing I'd like you to keep in mind is that the order of our premises is completely irrelevant. That is, if I have A and then I have B, I can write down B and A. But if it was B first and A second, I could still write down B and A. These rules are not telling us the order in which the premises must come, but rather just that you must have those premises available to you. So order is completely irrelevant. The last thing I wanted to point out is that our rules apply to whole lines and not parts of lines. And to explain what I mean by that, let me erase everything except for AND in here and just give an example. So suppose we've got a derivation that goes like this. Premise 1 is A arrow B. Premise 2 is A. And suppose, doesn't matter what we're trying to prove at this point, suppose we've gone several steps through in our proof, and we're now at line, say, 5, if you like. And suppose I did the following. Sorry. I want this to be C. So A, arrow B, and C. And now we're down at line 5, say, and I do the following. I say, well, I want to write down A and C, and that follows from 1 and 2 by and in. Because, after all, I've got A here, and I've got C here, and in says I can put them together with an and. That's not the way our and in rule works, because the A and the B have to be on the entire formula that's on a line. That is, you can't take a part of line 1 and put it together with line 2. What and in says instead is that you can take everything on line 1 and connect it to everything on line 2 with an and. So while this is incorrect, what you actually could do is write down something like this if you wanted. A, arrow B, and C. That does really follow from lines 1 and 2 by and in, but what I've written here does not. So just remember, our rules apply to whole lines, not to parts of lines. You can't take part of a line and put that together with something else. The rules apply to whole lines. All right, I think that about does it with our rules. What we're going to do in the next video is start applying these rules to prove and derive different arguments and show their validity.